So now we're going to look at the second part of the fundamental theorem of calculus. We looked at the first part, basically finding the area underneath the curve, and if you want to do that, you do your antiderivative, and then if I can talk, evaluate it from B back to A. So now, if you have capital F being your antiderivative, so in other words, you'd have to take your original function and integrate it. If you want to go ahead and do the derivative of capital F, you should get lowercase f. Basically, if you're doing the derivative in an integral, they should undo each other and cancel each other out. Because remember, doing the derivative and integration are opposite operations for the most part. Now, if we had original function with t in it, and we have a number here in the bottom with a variable x on the top, basically, we're going to have these two undo each other, and we're going to just take our x and put it in here. So what we're saying is because we are doing the derivative of an integral, your derivative should undo your integral, is really what we're saying. So for the most part, all we have to do, because your derivative undoes your integral, is we take this, plug it in for our variable here and for our variable here, and we would just get this. That's really what it's saying. But to help you understand this better, let's go ahead and take a look at this down here. If we were to go ahead and just do this integration part, you would get when you integrated that, you would get an expression with x in it minus an expression with 0, because remember, you have to integrate, and then you plug in your x minus what you get when you plug in 0. But now you'd be coming along to do your derivative of this. So if you're doing the derivative, your dx of this, well, you do your derivative of that expression with x, so that would undo your integral that you had. And so that would just be your original thing with just an x in it. And then you'd be doing your derivative of this thing that had 0 in it. So there's no variables, just 0 and maybe some functions. Well, derivative of anything with 0 in it, it's going to be a constant. Derivative of any constant, you know, is going to be 0. So it really comes down to just basically when you're doing the derivative of an integral with a variable up here, just taking that variable and plugging it in each one of your spots is really what it comes down to. Because once again, if you did integrate, you'd have something with a variable in it of x minus something with just a number in it. And well, if you do the derivative of that first part, it goes back to your original function with an x in it, and you do your derivative of something with just numbers, and that disappears. So what happens, though, when your upper bound is not just an x to the first, but, say, an x squared? Well, it's somewhat similar, but slightly different. So we're going to come along, and we're going to let u be equal to this upper bound of an x squared. Well, we'd then have to go ahead and find du. So we do the derivative of each side, and we would get du to be a 2x. So when we're doing this derivative of our integral, basically it would give us this. You'd put derivative of your integral. This is just u to the first, so it's going to go in for each variable here. So it would go in here, it would go in here, and then we just have to have your derivative of u with respect to x at the end. Well, if you plug in your x squared here, we would get this. Plug in your x squared here, we would get this. And well, what is your du dx, which is this? So for the most part, when you're dealing with this up here, you're still going to go ahead and take this and plug it in here and plug it in here. And then what this is the chain rule. The derivative of this is really what it boils down to. So if your upper bound is not just a nice normal x, you plug it in each spot, and then the dt means multiplied by the derivative of that. So in this case, it simplifies down to this. So that's the second part of the fundamental theorem of calculus. We're going to do one more thing here, and that's looking at total distance traveled. And we're going to look at total the displacement. Displacement is basically your area that you would have showing up right here. It'd be the area above, which we would have two areas above, and then the area below, which is negative, so that would make your overall area a little bit smaller. If you're looking for displacement, you can basically do it as one big integral from A to B, and the area below is subtracted, making it overall a smaller area. Total distance traveled, though, you have to break it into the parts that are above and the parts that are below. So total distance traveled, you do the parts that are above here, parts below, parts above, and total distance traveled is always positive, so it's really the absolute value of each one of those pieces is what it boils down to. So basically you figure out your three areas, make sure they're all positive by using absolute value, just add them together. So in other words, displacement is the total area, the net area, bound between A and B, where the area below is going to make the total area smaller because it's a negative area. Total distance traveled makes this area positive, makes this area positive, makes this area positive. So let's look at finding displacement and total distance here. So displacement, once again, is just your area of your original function. You're given your velocity function here, and you should remember that when you integrate velocity, you would get distance. So we're going to do just one integral of your whole function, and then we're going to just evaluate it like we were doing earlier here, increasing your exponent by 1, undoing the exponent, and so on, evaluating it by plugging in a 5 minus what you get when you plug in a 1, and so you get this. And in this case, our units would be feet because it says feet per second for your velocity. So displacement's pretty easy. You just do one big integral. But total distance is a little bit different. You have to look at, well, the part that's above we'll do as one integral. The part that's below we'll do as a separate integral. In this case, it switches from above to below right here at 4. So when we're doing this, just like we did with our absolute value before, we have to break it into two parts. From where it switches to positive to negative, where it would be 0, which would be right here at 4. So we have to do one integral from 0 to 4, plus another integral going from 4 all the way to 5. So we can do our integral of our function with our absolute value from 1 to 4, plus our integral of our function from 4 to 5 with our absolute value. We do our integration of this, our integration of this. Then we have to evaluate the first one, plug in our 4, minus what you get when you plug in 1. And then we're going to have to add when we evaluate this. Plug in your 5 minus what you get when you plug in your 4. Now in this case, your original one, your first one here, not your original, was a positive number, so your absolute value didn't do anything. When you evaluate the second one, it's a negative number, so your absolute value is going to do something, and it's going to make it then 45 over 4 plus a positive 7 over 12. So we get 71 over 6 feet for your total distance traveled.